A professional baseball pitcher throws a fastball at about 100 miles per hour. That ball weighs roughly 5 ounces. The kinetic energy, the energy of motion, is about 148 joules, enough to sting your hand if you catch it wrong, maybe break a finger. Now, let's accelerate that same baseball to 1% the speed of light. That's 6.7 million miles per hour. The kinetic energy is now 38 billion joules. That's equivalent to 9 tons of TNT. One baseball, 9 tons of TNT, enough to level a city block. Let's keep going. 10% the speed of light, same baseball. The energy is now equivalent to 43 kilotons of TNT, 3 times the Hiroshima bomb. One baseball has become more destructive than the weapon that ended World War II. Now 90% the speed of light. This is where physics gets obscene. That 5-ounce baseball now carries the kinetic energy of 1.5 million Hiroshima bombs. It's moving so fast that if it were launched from the moon, it would hit Earth in 1.5 seconds. There would be no warning, no defense, no time to pray. The impact would release 65 million megatons of energy. The dinosaur-killing asteroid, the one that ended the Cretaceous period and wiped out 75% of life on Earth, released roughly 100 million megatons. You've just matched an extinction-level asteroid impact with an object you could hold in your hand. Welcome to the terrifying world of relativistic kill vehicles, weapons so powerful that possessing them means you can destroy planets. The catch? Any civilization capable of traveling between stars automatically has access to this technology, and the math suggests we're less than a century away from building them ourselves. Here's what should keep you awake at night. These weapons are inevitable. They require no exotic materials, no antimatter, no fictional science, just speed. And in the cosmos, speed is easy. It's surviving in a universe where everyone has extinction weapons that's hard. This is Relativistic Kill Vehicles, the extinction weapons anyone can build. And by the end of this, you'll understand why the silence of the universe might not be a mystery at all. It might be a survival strategy.
Let's start simple. Kinetic energy is the energy an object has because it's moving. The formula is beautifully straightforward. E equals 1/2 mass times velocity squared. Energy equals 1/2 mass times velocity squared. It's been on every physics classroom wall for 300 years. But there's something sinister hiding in that formula. Notice that velocity is squared. That means if you double the speed, you don't double the energy, you quadruple it. Triple the speed, and you get 9 times the energy. This is exponential growth disguised as a simple equation. And exponential growth is always, always dangerous. Let's build our intuition with something familiar. A .22 caliber bullet weighs about 2.6 grams and travels at roughly 1,200 feet per second. The kinetic energy is around 140 joules. That's enough to penetrate skin and tissue, lethal at close range but not dramatically destructive. You could shoot a .22 into a wooden door and you'd get a hole, not an explosion, just a hole. Now let's move up the scale. An anti-tank round fired from an M1 Abrams weighs about 10 kilograms and travels at 5,600 feet per second. The kinetic energy is now 5 megajoules. That's enough to punch through a foot of steel armor. Notice what happened. We increased the mass by 4,000 times and roughly quadrupled the velocity. The result? The energy increased by about 35,000 times. This is how kinetic weapons work. They don't rely on chemical explosives or nuclear fission. They rely on physics doing the dirty work. Velocity is a multiplier of violence. The US military has experimented with this concept for decades. They're called rods from God, hypothetical orbital kinetic bombardment weapons. The idea is simple. Drop a tungsten telephone pole from orbit. By the time it hits the ground, it's traveling at roughly 10 times the speed of sound. No explosives needed. The impact releases energy equivalent to a small tactical nuke. A 20-foot tungsten rod weighing about 11,000 kilograms, falling from low Earth orbit, would hit with approximately 11.5 gigajoules of energy. That's equivalent to roughly 2.75 tons of TNT, enough to destroy a bunker complex or wipe out a city block. And it's completely non-nuclear, which means it sidesteps all sorts of international treaties and taboos. But here's the thing. Orbital kinetic weapons are the minor leagues. They're working with velocities measured in kilometers per second. The real nightmare begins when you start thinking in terms of thousands of kilometers per second, tens of thousands, hundreds of thousands. In space, there's no air resistance, no friction. Once you accelerate something, it just keeps going at that speed until something stops it. And if you can keep accelerating, if you have enough energy and enough time, you can push objects to truly obscene velocities. The speed of light is 299,792 kilometers per second. That's 670 million miles per hour. It's the cosmic speed limit, the ultimate velocity. Nothing with mass can reach it, but you can get close, very close. And here's where the math turns from scary to apocalyptic. When objects approach the speed of light, Einstein's theory of special relativity kicks in. That simple kinetic energy formula we started with, E equals 1/2 mv squared, that's actually just an approximation that works at low speeds. At relativistic speeds, the real formula includes something called the Lorentz factor. The Lorentz factor represents how time dilation and length contraction affect moving objects, but for our purposes, what matters is that it also affects energy. The relativistic kinetic energy formula is kinetic energy equals mass times the speed of light squared times the Lorentz factor minus 1. Translation: as you approach light speed, the energy doesn't just increase exponentially, it increases asymptotically. It shoots toward infinity. A small increase in velocity near light speed produces a massive increase in energy. Let's use a real example. Take 1 kilogram, about 2.2 pounds, roughly the weight of a small laptop. At 1% light speed, 4.5 times 10 to the 13 joules. That's 10.75 kilotons of TNT, almost the Hiroshima bomb. At 10% light speed, 4.56 times 10 to the 15 joules. That's 1.09 megatons, 70 Hiroshima bombs. At 50% light speed, 1.53 times 10 to the 16 joules. That's 3.66 megatons, 240 Hiroshima bombs. At 90% light speed, 1.03 times 10 to the 17 joules. That's 24.6 megatons, 1,640 Hiroshima bombs. 1 kilogram, the weight of a textbook, moving at 90% light speed, carries 1,640 times the destructive power of the weapon that incinerated a city and killed 140,000 people. And we're just getting started. The asteroid that killed the dinosaurs, the Chicxulub impactor, was roughly 10 kilometers in diameter and weighed about 1 trillion kilograms. It was traveling at roughly 20 kilometers per second, about 45,000 miles per hour. Fast for human standards, but cosmically speaking, it was crawling. The impact released an estimated 100 million megatons of TNT equivalent. It punched through the atmosphere in less than a second, vaporized trillions of tons of rock, created a crater 180 kilometers wide, triggered magnitude 11 earthquakes, spawned tsunamis over a kilometer high, and ejected so much debris into the atmosphere that the entire planet was plunged into a years-long winter. 75% of all species went extinct. Now, here's the punchline. You could match that asteroid's destructive power with a projectile the size of a car. Traveling at 90% light speed, a Honda Civic accelerated to relativistic speeds carries the same kinetic energy as the rock that ended the age of dinosaurs. Think about that. The most famous extinction event in Earth's history, the cosmic catastrophe that became synonymous with apocalypse, could be replicated with an object small enough to park in your garage. All you need is speed. And here's the really fun part. We already know how to achieve those speeds. Not theoretically, not speculatively. We've had the engineering proposals on the books since the 1960s. The question isn't whether relativistic kill vehicles are possible. The question is how long until someone builds one. And more importantly, what do you do when you live in a universe where every civilization with a space program has access to extinction weapons? Because here's the terrifying truth. We're not talking about advanced alien technology. We're talking about physics that any species discovering calculus and electromagnetism will eventually master. This is inevitable technology. And inevitable technology means inevitable danger. The year is 1958. Dwight Eisenhower is president. Elvis Presley is drafted into the Army. NASA is founded. And a physicist named Freeman Dyson starts working on something absolutely insane, a spaceship propelled by nuclear bombs. The project was called Orion, and the concept was simple, in the way that jumping out of an airplane without a parachute is simple. You build a massive shock absorber plate on the back of your spacecraft. You throw nuclear bombs out behind you, the bombs detonate, the explosion hits the plate absorbs the impact and transfers the momentum to the ship. You accelerate. Then you throw another bomb, and another, and another. One nuclear explosion every second, pushing your spacecraft faster and faster. It's the most brute force approach to space propulsion ever seriously considered, and mathematically, it works. The Orion design team calculated that a ship weighing 10,000 tons could reach Mars in 4 weeks using about 800 nuclear devices. The same ship could reach the outer solar system in a few years, and with enough bombs and a big enough ship, you could theoretically push velocities to a few % of light speed. Project Orion was ultimately canceled in 1965, partly because of the Nuclear Test Ban Treaty, partly because it was politically radioactive, pun intended, and partly because the engineering challenges were enormous. But the physics was sound. Nuclear pulse propulsion works. We could have built it. And here's the thing. Orion represented 1960s technology, chemical rockets, fission bombs, mechanical shock absorbers. It was hilariously primitive by today's standards, and it could still reach 3 to 5% of light speed with enough fuel. Imagine what you could achieve with better technology. Let's talk about fusion drives. Fusion, the process that powers the sun, releases roughly 10 times more energy per kilogram than fission. A fusion-powered rocket could, in theory, achieve exhaust velocities of 10 to 20% the speed of light. The challenge is getting the fusion reaction to work reliably. We're still struggling with that on Earth. But if you can master controlled fusion, and we're getting closer every year, you suddenly have access to propulsion systems that can push spacecraft to truly relativistic speeds over time. Then there's the breakthrough Starshot project, announced in 2016 and funded by billionaire Yuri Milner and supported by Stephen Hawking. The goal? Send tiny spacecraft to Alpha Centauri using laser propulsion. The concept is elegant. You build a spacecraft the size of a microchip, maybe a gram in mass. You attach it to an ultra-lightweight reflective sail, then you hit that sail with an absolutely enormous laser array from Earth. The laser pushes against the sail, accelerating the spacecraft. The plan calls for a 100-gigawatt laser array, roughly the output of 100 large power plants, focused on a sail 4 meters across. With sustained laser thrust, the spacecraft would accelerate to 20% the speed of light in about 10 minutes. 20% of light speed, from a standstill, in 10 minutes. At that velocity, the probe would reach Alpha Centauri, 4.37 light-years away, in about 20 years. That's interstellar travel using today's theoretical technology. No warp drives, no wormholes, just very powerful lasers and very lightweight spacecraft. Now, here's where it gets uncomfortable. That same technology, laser propulsion, can accelerate more than just microchip probes. It can accelerate anything with a reflective surface, including weapons. Imagine a 1-kilogram tungsten projectile with a laser sail attached. You hit it with your 100-gigawatt laser array, you accelerate it to 20% light speed, you detach the sail, the projectile continues at that velocity, about 60,000 kilometers per second, until it hits something. Impact energy, 1.8 times 10 to the 15 joules. That's 430 kilotons of TNT, 28 Hiroshima bombs from a 1-kilogram object, and you can build dozens of them. Hundreds, thousands. Congratulations, you've just turned a scientific exploration project into a weapons platform capable of destroying cities from across the solar system. And the terrifying part? This technology is being seriously developed right now. Breakthrough Starshot is a real project with real funding.
But wait, there's more. Let's talk about antimatter propulsion, the holy grail of relativistic travel. When matter meets antimatter, they annihilate each other with 100% conversion of mass to energy. Einstein's famous equation, E equals mc squared, in its purest form. 1 kilogram of matter plus 1 kilogram of antimatter produces 1.8 times 10 to the 17 joules of energy. That's 43 megatons of TNT from 2 kilograms of fuel. For reference, chemical rockets convert about 0.00001% of their fuel mass to energy. Fission bombs convert about 0.1%. Fusion bombs convert about 0.3%. Antimatter converts 100%. It's the most energy-dense fuel theoretically possible. A spacecraft powered by matter-antimatter annihilation could theoretically reach 50 to 90% of light speed with a reasonable mass ratio. You could cross the solar system in hours, reach nearby stars in years instead of millennia. The problem, antimatter is absurdly expensive to produce. CERN's particle accelerators can create a few nanograms per year. The current cost is estimated at $62.5 trillion per gram. At that price, you're not building antimatter drives. You're not building anything. But that's today. 1,000 years ago, aluminum was more valuable than gold because we couldn't produce it efficiently. Then we figured out electrolysis, and now aluminum is so cheap we wrap our sandwiches in it. If we develop better methods for antimatter production, magnetic confinement, improved particle accelerators, space-based facilities powered by solar energy, the cost could drop from trillions per gram to millions per gram, then thousands, then dollars. And once antimatter becomes economically viable as a propulsion fuel, it becomes economically viable as a weapons fuel, because a matter-antimatter reaction doesn't care whether it's happening in a rocket engine or strapped to a kinetic projectile. 1 gram of antimatter, about the weight of a dollar bill, releases 43 kilotons of energy when it annihilates. That's 3 Hiroshima bombs. In your pocket.
1 kilogram of antimatter, 43 megatons. That's the largest nuclear weapon ever tested, the Soviet Tsar Bomba, from a fuel source the size of a water bottle. Now imagine a civilization that can mass-produce antimatter. They don't need to build giant nuclear arsenals with expensive enrichment facilities and political complications. They just need particle accelerators and magnetic bottles, and suddenly they have unlimited extinction weapons. But let's bring this back to Earth, literally. We don't need antimatter drives to create devastating kinetic weapons. We just need better electromagnetic launchers. The U.S. Navy has been testing electromagnetic railguns since the 1990s. These weapons use powerful magnetic fields to accelerate projectiles to hypersonic speeds, Mach 7 and beyond. No chemical propellant, no explosives, just electricity and magnetism. The latest prototypes can fire a 10-kilogram projectile at Mach 7, about 2.4 kilometers per second. The kinetic energy is roughly 29 megajoules, equivalent to about 7 kilograms of TNT. That's enough to punch through several feet of concrete and steel. The range is over 100 miles. The projectile arrives at the target in seconds. There's no way to intercept it because it's not a missile, it's just a hunk of metal moving really, really fast. And because there's no explosive payload, it's cheaper than traditional munitions. Now scale this up. Put a railgun in orbit. Power it with a nuclear reactor or massive solar arrays. Engineer it to achieve escape velocities, 11.2 kilometers per second just to leave Earth's orbit. Then keep scaling. A railgun accelerating a projectile to 100 kilometers per second, 1,000 kilometers per second, 10,000 kilometers per second. Each increase requires more power, better materials, larger systems. But there's no fundamental physical barrier, it's just engineering. Some proposals call for mass drivers, essentially ultra-long railguns built in space, possibly on the moon or asteroids. You could build a launcher hundreds of kilometers long, gradually accelerating payloads to enormous velocities. On the moon, with no atmosphere and lower gravity, you could build a mass driver that accelerates cargo to 10 to 20 kilometers per second using solar power. That's enough to send supplies to Earth orbit, Mars, or anywhere in the solar system. It's economically brilliant for space colonization. It's also a weapon, because if you can throw a supply container at Mars, you can throw a tungsten rod at Earth. Same technology, different target. So, let's review. Nuclear pulse propulsion, viable with 1960s technology, could reach a few % of light speed. Fusion drives, better performance, could reach 10 to 20% light speed. Laser propulsion, already being developed, 20% light speed demonstrated concept. Antimatter drives, currently too expensive, but physics allows 50 to 90% light speed. Mass drivers and railguns, scale them up enough and you're accelerating projectiles to significant fractions of light speed. Every single one of these technologies is being researched right now, not by alien civilizations, by us, by humans, in universities, government labs, and private companies. The engineering challenges are enormous, but they're just that, engineering challenges, not physical impossibilities. And history shows that once we figure out the fundamental principles, the development curve is exponential. The Wright brothers flew in 1903. We landed on the moon in 1969. 66 years from the first powered flight to humans walking on another world. Nuclear fission was discovered in 1938. The first atomic bomb was tested in 1945. 7 years from scientific discovery to deployed weapon. The first iPhone was released in 2007. By 2024, there are billions of smartphones more powerful than the computers that sent astronauts to the moon. 17 years from introduction to ubiquitous global saturation. So when do we build relativistic kill vehicles? Not if, when, because the technology is inevitable. We're already on the path. All that's left is time, resources, and motivation. And in a universe where traveling between stars requires relativistic velocities, every species that achieves spaceflight automatically gains access to planet-killing weapons. It's not a choice, it's a consequence of physics. Which brings us to the nightmare question. What happens when you have a weapon you can't defend against, can't intercept, and can't survive?
Let's do some apocalypse math. Not because it's fun, though there's a dark fascination to it, but because understanding the scale of destruction is essential to understanding why these weapons represent an existential threat unlike anything humanity has faced before. Scenario: a hostile civilization, or hell, a hostile human faction in the future, launches a 1-kilogram tungsten projectile at Earth from, say, 1 light-year away. They've accelerated it to 90% the speed of light using whatever propulsion technology they prefer. Laser sail, antimatter drive, doesn't matter. It's moving at 270,000 kilometers per second. Can we detect it? Maybe. Probably not. At 90% light speed, the projectile covers 1 light-year in about 1.1 years. But we only detect it when the light from its launch reaches us, and that light is traveling at light speed, only 10% faster than the projectile itself. So if the light reaches us, say, 12 days before the projectile does, that's our warning window. 12 days to realize we're about to be hit by an extinction weapon. 12 days to do what exactly? Intercept it? With what? Our fastest spacecraft travel at tens of kilometers per second. This projectile is traveling at 270,000 kilometers per second. You'd need to launch your interceptor years in advance, predict exactly where the projectile would be, and somehow destroy or deflect an object moving at relativistic speed. Even if you had a nuclear warhead detonating right next to the projectile, the blast would propagate at maybe 10 kilometers per second. The projectile would fly through the explosion faster than the shock wave could expand. It would barely notice. Evacuate? Where? The entire planet is the target. There's nowhere to run. So let's say we've exhausted our non-existent options, and the projectile enters Earth's atmosphere. This is where physics becomes truly nightmarish. At 90% light speed, the projectile's relativistic mass has increased significantly due to the Lorentz factor. Its effective mass is now about 2.29 kilograms instead of 1 kilogram. But more importantly, the kinetic energy is astronomical, 1.03 times 10 to the 17th joules. That's 24.6 megatons of TNT. The largest nuclear weapon ever tested, the Soviet Tsar Bomba, was 50 megatons, but it required a bomb the size of a small house and weighed 27 tons. This is half that yield from an object you could hold in your hand. As the projectile screams through the atmosphere, it compresses the air in front of it so violently that the air itself ignites. The temperature spikes to tens of thousands of degrees, hotter than the surface of the sun. The projectile is effectively pushing a wall of superheated plasma ahead of it. The sonic boom, if you can even call it that, is a shockwave moving at relativistic speeds. Everything in its path is vaporized instantly. The atmosphere doesn't have time to move out of the way, so it gets compressed to nuclear densities. Then it hits the ground. Let's say it hits in the middle of the ocean, because most of Earth's surface is water. The projectile punches through several kilometers of water in microseconds, barely slowing down, and slams into the oceanic crust. The kinetic energy converts to heat instantaneously. The water within 100 meters vaporizes, not boils, vaporizes, instantly. The rock at the impact site doesn't melt or crack, it vaporizes too, converting from solid to plasma in nanoseconds. A crater begins forming. The pressure wave propagates outward at hypersonic speeds, pulverizing everything in its path. The ocean floor buckles and heaves. Millions of tons of water are displaced upward, forming a wave that would make any tsunami in recorded history look like a ripple in a bathtub. The wave radiates outward at 700 to 800 kilometers per hour. If the impact occurs in the mid-Atlantic, the wave reaches the coasts of Europe, Africa, and the Americas within hours. Cities like New York, London, Lagos, Rio de Janeiro are obliterated by walls of water 100 meters or more. But that's just the local effect. The seismic shock wave from the impact propagates through the entire planet. We're talking about a magnitude 9 or magnitude 10 earthquake, strong enough to trigger secondary quakes along every fault line on Earth. Buildings collapse, infrastructure fails, millions die in the first hour. Meanwhile, the vaporized rock and water, millions of tons of it, has been blasted into the atmosphere. Some of it reaches escape velocity and flies off into space. Most of it rains back down as superheated debris, igniting fires across entire continents. The thermal radiation from the impact itself is enough to cause third-degree burns to exposed skin hundreds of kilometers away. Forests ignite, cities burn. The smoke and ash begin rising into the stratosphere, creating a cloud that spreads around the planet within days. And then comes the climate catastrophe. All that debris in the atmosphere blocks sunlight. Temperatures plummet. Photosynthesis shuts down. Crops fail globally. We enter an impact winter that could last months or years depending on how much material was ejected. Conservative estimate, 1 billion dead within the first week from the immediate impact, tsunamis, earthquakes, and fires. Another billion over the following months from starvation, disease, and societal collapse. Much more. This is an extinction-level event from a 1-kilogram projectile. Now, scale up, because there's no reason an attacker would limit themselves to 1 kilogram. Why not 10 kilograms, 100 kilograms, 1,000 kilograms? A 1,000-kilogram projectile at 90% light speed carries 1.03 times 10 to the 20th joules. That's 24,600 megatons, roughly 500 times the Tsar Bomba. It's getting close to the dinosaur-killing asteroid impact. One object, the size of a small car, could trigger a genuine mass extinction. Or forget scaling up individual projectiles, just launch more of them. 10 1-kilogram projectiles, 100, 1,000. Spread them out so they hit different parts of the planet over the course of a few hours.
Earth's surface becomes a shooting gallery. Oceans boil, continents burn. The atmosphere is choked with debris. The planet's entire surface is sterilized. Nothing larger than bacteria survives. Maybe not even bacteria. Here's the truly horrifying calculation. The energy required to completely shatter Earth, not just extinguish life, but literally blow the planet apart into fragments, is estimated at about 2 × 10⁻32 joules. That's the gravitational binding energy of the entire planet. To deliver that much energy with a projectile at 90% light speed, you'd need about 2 billion tons of mass. That sounds like a lot, but it's not. It's roughly the mass of a small asteroid, maybe 1 kilometer in diameter. Humanity has tracked thousands of asteroids that size or larger. A sufficiently advanced civilization with asteroid mining capabilities could capture one of those asteroids, hollow it out, install engines, and accelerate it to relativistic speeds. The result is a planet-cracking weapon built from materials already floating around in space. The Death Star from Star Wars destroyed planets with a superlaser powered by kyber crystals in fictional physics. That's fantasy. A relativistic asteroid is reality, and it's more destructive, and it requires no magic crystals or planet-sized space stations. Could we build one today? No. But could a civilization a few hundred years more advanced than us build one? Almost certainly yes. The physics is straightforward. The engineering is just a matter of scale and energy, both of which improve with technological development. We went from horse-drawn carriages to nuclear weapons in 100 years, from the first airplane to landing on the moon in 66 years, from room-sized computers to smartphones in 50 years. Extrapolate that curve forward another 200 years, and planet cracking becomes plausible. Now here's the part that should make your skin crawl. None of this is secret or classified. The physics is well understood. The propulsion technologies are being actively researched. The potential applications, peaceful and otherwise, are openly discussed in academic papers and at conferences. In 1950, physicist Freeman Dyson, yes, the same guy behind Project Orion, was already thinking about relativistic weapons. In his later writings, he speculated about what he called relativistic projectiles and their implications for interstellar warfare. He understood the threat. In 2002, astrophysicist Martin Beach published a paper titled Terraforming versus Relativistic Destructive Probes, discussing exactly this scenario. He calculated the energies involved and concluded that any civilization capable of interstellar travel could easily destroy planets. Space agencies and military planners are aware of this. They just don't talk about it publicly very often, because what's the point? There's no defense. Mutual assured destruction doesn't work when the weapon travels at 90% light speed and gives you 12 days warning at best. This is the ultimate first strike weapon. If you suspect another civilization might attack you, the incentive is to attack them first. Hit them before they can hit you, because there's no defense, no deterrence, no possibility of surviving if you're on the receiving end. Game theorists call this a defection-dominant scenario. Trust is irrational. Cooperation is suicidal. The only logical strategy is to strike first, or hide so well you're never found. And that brings us to the existential question that's been lurking beneath this entire discussion. If these weapons are so inevitable, so accessible to any spacefaring civilization, then why haven't we been hit yet? Where is everyone? And more importantly, are they hiding from something?
In 1950, physicist Enrico Fermi asked a question that's haunted scientists ever since. Where is everybody? The Milky Way galaxy contains between 100 and 400 billion stars. Billions of those stars have planets. Millions of those planets are in the habitable zone, where liquid water can exist. Even if intelligent life is incredibly rare, 1 in a million, there should be thousands of civilizations in our galaxy alone. We've been listening for alien signals since the 1960s. We've scanned thousands of star systems. We've searched for technosignatures, radio transmissions, laser communications, anything that might indicate the presence of advanced technology. Silence. Complete silence. The cosmos is eerily, unsettlingly quiet. Scientists have proposed dozens of solutions to this paradox. Maybe life is rarer than we think. Maybe intelligence is a cosmic fluke. Maybe advanced civilizations destroy themselves. Maybe they transcend to higher dimensions. Maybe they're all living in simulated realities and don't care about the physical universe anymore. But there's another explanation, proposed by Chinese science fiction author Liu Cixin in his novel The Dark Forest. It's called the Dark Forest Hypothesis, and it's the most chilling solution to the Fermi paradox ever conceived. The hypothesis goes like this: the universe is a dark forest. Every civilization is a hunter moving silently through the trees. If you make noise, if you broadcast your location, another hunter might find you. And because you can't know if that hunter is friendly or hostile, and because the distances involved make communication and trust impossible, the safest strategy is to shoot first. Imagine you're an advanced civilization. You detect a radio signal from a nearby star system. What do? You can't communicate meaningfully. The light speed delay means decades between messages. You can't assess their intentions. You can't determine if they're peaceful or hostile. You can't predict their technological development. But you know one thing. If they're hostile, and if they continue developing, they might eventually become a threat to you. They might build relativistic kill vehicles. They might decide that your star system has resources they want. They might simply eliminate potential competitors. So what's the rational response? You eliminate the threat while it's still weak. You launch relativistic kill vehicles at their home planet before they can do the same to you. You commit genocide not out of malice, but out of cold, rational self-preservation. And here's the nightmare twist. Once one civilization adopts this strategy, every civilization must adopt it. Because if you're the only peaceful species in a galaxy full of trigger-happy hunters, you go extinct fast. The result is cosmic silence. Everyone's hiding. Transmitting into space is suicide. Making your presence known is like lighting a campfire in that dark forest. You'll attract something, and there's a good chance it'll kill you. Which means humanity might have made a catastrophic mistake. For the past century, we've been broadcasting radio and television signals into space. Those signals are now 100 light-years out, reaching thousands of star systems. We've essentially been screaming our location into the void. If there's a civilization within that 100 light-year bubble, they know we're here. And if they subscribe to dark forest logic, the relativistic kill vehicles are already on their way. We just won't know it until they arrive. And we're still doing it. Projects like METI, Messaging to Extraterrestrial Intelligence, are deliberately beaming powerful radio signals at nearby star systems, trying to make contact. Some scientists think this is a wonderful idea. Others think it's insane. Stephen Hawking warned against this. In his words, if aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. That's actually optimistic. Columbus wanted resources and territory. A civilization with relativistic weapons doesn't need to invade. They can just eliminate potential threats from a safe distance. Relativistic kill vehicles are the perfect dark forest weapon. They're fast enough that you can't flee. They're destructive enough that you can't survive. And they're launched from light years away, so the attacker is never in danger. The first strike advantage is absolute. If you know where an enemy is and you can build RKVs, you win. They can't defend. They can't retaliate if they're dead. And if you're worried about retaliation, you simply make sure the first strike is comprehensive enough that nothing survives. Now let's talk about civilization types. The Kardashev scale classifies civilizations based on energy usage. Type 1 harnesses the energy of its planet. Type 2 harnesses the energy of its star. Type 3 harnesses the energy of its galaxy.
Humanity is currently about 0.73 on the Kardashev scale. We're not even Type 1 yet. We're a Type 0.73 civilization playing with nuclear weapons and contemplating interstellar travel. A Type 1 civilization, one that has fully mastered planetary engineering, would have access to enormous energy sources. They could build particle accelerators the size of continents. They could produce antimatter in industrial quantities. They could construct mass drivers on multiple worlds. For a Type 1 civilization, building relativistic kill vehicles isn't a massive undertaking. It's just infrastructure. They could churn out planet killers the way we manufacture cars. A Type 2 civilization, one that's built a Dyson swarm to capture most of its star's output, operates on a scale we can barely imagine. They have access to 10 to the 26th watts of power continuously. That's 2 billion times more energy than humanity currently uses.
With that much energy, you could accelerate truly massive objects to relativistic speeds. Not 1 kilogram projectiles, not 1,000 kilogram asteroids, multi-kilometer objects, moons. You could weaponize actual moons and throw them at enemy star systems at 99.99% light speed. Or you could skip the kinetic weapons entirely and just build an ultra-powerful laser. Concentrate your star's entire output into a beam and aim it at the enemy. They'd be vaporized before they even knew they were under attack. This is what's called the Great Filter in discussions of the Fermi paradox. The idea is that there's some barrier, some filter that prevents civilizations from becoming widespread in the galaxy. Most proposed filters are things like nuclear war, climate catastrophe, or runaway AI. But maybe the Great Filter isn't self-destruction. Maybe it's mutual destruction. Maybe civilizations don't destroy themselves, they destroy each other. The moment you become visible in the cosmos, you become a target. And the moment you achieve spaceflight, you have the tools to make planet-killing weapons. Think about the timeline. From radio transmission to spaceflight takes about 100 years based on human development. From spaceflight to relativistic weapons, maybe another 100 to 200 years. So you have a 200-300-year window where you're both visible and vulnerable. If there are older, more advanced civilizations out there, they've had millions or billions of years to spread throughout the galaxy and set up monitoring systems. The moment you start broadcasting, they detect you, and if they operate on dark forest principles, they immediately calculate whether you'll be a threat. If the answer is yes, or even maybe, they launch the RKVs. Impact arrives 10, 50, 100 years later, depending on distance. Your civilization never sees it coming. One moment you're building warp drives and writing poetry. The next moment, your planet is a cooling ball of molten slag. And the galaxy remains silent, because the only civilizations that survive are the ones that never make noise, the ones that never expand beyond their home system, the ones that hide. So, what do? We're already visible. Our radio signals have been propagating for a century. If someone out there is listening, they know about us. Do we stop broadcasting? Do we go silent and hope we're ignored? Or do we do the opposite? Do we expand as fast as possible, spread to Mars, the outer planets, nearby star systems, diversify our civilization across multiple worlds so that no single strike can eliminate us? Do we accelerate our own development of relativistic weapons so we can strike first if we detect a threat? Do we embrace the dark forest logic and become hunters ourselves? Or do we reject the entire premise? Do we insist that cooperation is possible, that trust can exist, that the universe doesn't have to be an endless arms race of extinction weapons? These are the questions that will define humanity's future if we survive long enough to become a spacefaring species. And they're questions with no easy answers. Because here's the thing about relativistic kill vehicles. They're not speculative technology from a distant future. They're inevitable consequences of physics and engineering that any civilization will discover. And that means somewhere out there, someone might already be building them.
We're a young species on a small planet, screaming into a dark forest, and we have no idea what's listening.
So let's talk about what happens next. Not what we hope happens, not what we want to believe, what actually happens when relativistic kill vehicles become reality. Military strategists call it mutually assured destruction, MAD. It's the doctrine that kept the US and Soviet Union from launching nuclear weapons at each other during the Cold War. If you nuke me, I'll nuke you back, and we both die. Therefore, nobody launches. MAD works when both sides have second strike capability, the ability to retaliate even after being hit first. Nuclear submarines hiding in the ocean, bombers constantly in the air, missile silos hardened against attack. You can't eliminate your enemy's entire arsenal in one strike, so they can always hit back. Relativistic kill vehicles break that logic. A comprehensive first strike at 90% light speed doesn't leave anything intact. No submarines, no silos, no cities, no civilization. Dead before you know you're under attack. Second strike capability requires surviving the first strike, but you can't survive an RKV bombardment, which means deterrence doesn't work, which means the rational strategy is always to strike first. Unless you're spread out. If your civilization spans multiple star systems, if you've colonized dozens or hundreds of worlds, then one strike can't eliminate you. Some of your colonies survive, and they can retaliate. This is what's called distributed deterrence. You're so widespread that destroying you requires hitting dozens of targets simultaneously across light years of space. That's much harder to coordinate, and it gives you time to detect the attack and strike back. Which means every spacefaring civilization is in a race. Expand fast enough to become unkillable before someone tries to kill you. Spread to enough star systems that you can't be wiped out by a single adversary. And once that race begins, it doesn't stop, because if you stop expanding, you become vulnerable. If someone else keeps expanding while you stand still, eventually they'll surround you, outnumber you, and have the resources to launch enough RKVs to hit all your worlds at once. The logical endpoint is a galaxy dominated by one or two massive civilizations that have expanded so aggressively that nobody else can challenge them. Everyone else either got absorbed, destroyed, or is hiding in the shadows. And we're nowhere close to that level. We're on one planet, our entire species, all our history, all our potential, concentrated in one fragile biosphere orbiting one star. If someone wanted to eliminate us, it would take one strike, just one. Optimistic estimates say we might have self-sustaining colonies on Mars by 2100, maybe orbital habitats in the asteroid belt by 2550, interstellar probes by 2200, actual colony ships to nearby stars by 2300. That's at least 250 years before we're even beginning to be distributed. 250 years of being a single planet species broadcasting our existence to the universe. 250 years of being one RKV away from extinction. Our radio signals have reached about 100 light-years so far. That sphere is expanding at the speed of light, meaning about 15,000 star systems have potentially heard us by now. With every year that passes, thousands more stars enter our announcement sphere. If even 0.1% of star systems harbor intelligent life, that's 15 civilizations that know we exist. If even one of them operates on dark forest principles, we're on borrowed time. Think about it from their perspective. Eliminating us costs them what? The resources to build and launch an RKV? For an advanced civilization, that's trivial. The benefit? One less potential competitor in the galaxy. One less civilization that might, centuries from now, become a threat. It's not personal, it's not evil, it's just math. Ruthless, survival-driven math that says the safest bet is to eliminate potential threats before they become actual threats. So, here are our options. 1. Accelerate space colonization as fast as physically possible. Get to Mars. Get to the moons of Jupiter and Saturn. Get to Alpha Centauri. Spread out before someone finds us.
2. Shut up. Stop transmitting into space. Dismantle medi-projects. Go silent and hope we're ignored or overlooked among the billions of other worlds. 3. Develop detection and defense systems. Build massive telescope arrays to watch for incoming relativistic objects. Develop laser grids that can vaporize or deflect incoming projectiles. Good luck with that. The physics is brutal. 4. Build our own relativistic kill vehicles. Develop the technology and production capacity to strike back if threatened. Become a player in the great game rather than a victim. Or 5. Some combination of all the above. Expand, hide, prepare, and arm ourselves. Become a civilization that's too spread out to eliminate, too quiet to easily find, and too dangerous to attack lightly. The clock is ticking. We've already announced ourselves. The light carrying our existence is spreading at 186,000 miles per second. We can't take it back. Maybe we're alone. Maybe the universe is empty and all these fears are pointless. Maybe we'll expand to the stars and never meet another living soul. Or maybe we're being watched right now. Maybe someone out there is running the calculations, estimating our technological development, predicting when we'll become a threat, deciding whether to fire. We are a young species with old dreams. We want to explore. We want to meet other minds among the stars. We want to believe the universe is a place of wonder and discovery. But physics doesn't care what we want, and evolution favors the paranoid. Welcome to the dark forest. Try not to make too much noise. The question isn't whether relativistic kill vehicles will be built. The question is whether we'll be the ones building them, or the ones they're aimed at.